So, welcome you all to this live session 6 of course Energy, Solar Energy Engineering and Technology. And this course is taught by Professor Pankaj Kalita. And I'm Rohit, I'm junior scholar. I will be taking the live session 6 of this course. So, basically, we'll be discussing and having a recap of the previous lecture videos and lecture slides. Apart from that, we will also have a discussion on the assignment questions from previous run of this course. So I'm sure that you guys will get a good understanding of the concepts in this live session, and also will be able to grab and solve the questions upfront. Otherwise, if you have any doubts or queries, please raise it in the live session, or you can also write in the white box. I will read the questions and I will answer it accordingly. Okay, so I'm starting this session. So let me first have a recap of the what was taught. Okay, so first thing is that in the previous week we were talking about the standalone systems. So what are standalone systems? Standalone systems are those systems which are actually uh, on their own. They are not connected to the grid. They are catered to a specific household or like pumping system. The other thing is that the functioning this week we will be studying the grid connected photovoltaic system, and we'll be discussing the functional layout of a grid connected photovoltaic system and different components of a grid connected photovoltaic system. So what is a grid connected photovoltaic system? This is the first question which comes to your mind. So basically a grid connected photovoltaic system is made up of an array of panels, and they are mounted on metallic supports and they are integrated into a building. And these panels can be connected in series, like one after another, and they are connected to a single voltage, or when the voltage gets divided up and the current produced is summed up. Okay, or okay, no, the same current flows through in series, okay, or in parallel, like one after another in layers, okay, to achieve optimal voltage and current. Okay, and generally the operating voltage of an array of panel is around 150 to 400 volt DC for small systems and 400 to 7 volt DC for inverters of 10 to 500 kilowatt. The maximum voltage is generally limited by problems of insulated panels to avoid any current leakage. Okay, so that's why the maximum voltage is actually accepted by inverter. So these things have to be kept in mind. So also the inverter is actually equipped with MPPT system, like we studied in the last lecture weeks also. The MPPT systems are multi-power point tracking system that constantly adjusts the entry voltage, which vary accordingly to the temperature and solar radiation. So what I will do, I will not discuss each and every slide here. I will go through the important slides and I will try to search for the numericals that can be solved with the help of those slides. So these are the basic grid connected PV photovoltaic systems. There is a photovoltaic array, then there is a DC inverter, and it provides electricity through the household. Then this household has a net meter. Net meter is actually whatever extra you are producing, it is feeding it to the grid. So whatever extra you sell to the grid, it gets deducted from the electricity bill that the grid charges you or the distribution company charges you. So it works in two way, like this way and this way also. So there are two types of electrical designs for photovoltaic power system, like without battery backup and with battery backup. So these are pretty simple. The one on the right hand side actually shows with a battery storage capacity system. Also, there can be various layout of grid connected PV system, like combiner box can be there where all the system get connected and then it is fed to inverter. Otherwise, a single system can be connected to input and the input is fed to the AC switch gear. So, what are this is a very important slide. So, what are different components of the PV plant? So, there are PV modules, power conditioning units, So what are power conditioning units? They basically convert the DC to AC and to have a similar voltage what grid is providing us with the same frequency. We have cables, combiner boxes and connectors. Then also there are several mechanical components to support the structure like module mounted structure, mounting foundation, and there are power monitoring systems like SCADA, weather station. Somebody wants to join. I feel that. Okay. So commercially available PV photovoltaic modules are classified into two types. Is there any question or something? Nisit raised hand. Yeah, Nisit, do you have any question? Which is the device used to sync? Hmm. Okay, okay, I understood your question. So there are power conditioning units. Okay, so there are power conditioning units in which there is some electronic equipment that actually sync the voltage of the grid connected system, grid with the this solar photovoltaic produced system. Hi, it is not an integral part of the system because whatever system which you have seen is mostly standalone system. A grid connected system is actually totally different from a standalone system. It does have many other components that are separated, not with the inverter but adjacent to the inverters, you can say. Okay. Yeah, so that's why we have power conditioning units. Okay, thank you. When we talk about commercially available photovoltaic modules, so they are classified into two types. So these things, I think they are also covered in the previous lectures. I won't go into detail. One is single or monocrystalline silicon solar cells. So wafers are basically arranged in a linear pattern, and then we have multi or polycrystalline silicon solar cell. So the wafers are actually fragments of silicons are melted together to form wafers there. Okay, and in monocrystalline the silicon is in the form of bars and cut into wafers. Okay, you can see from here they are in the form of bars, and here you can see there is a like melting together and fusing together to form the wafers. Okay, so these things are actually most of you know what should be the criteria, but expect a question in the assignments or exam from these type of things. Okay, so what can be the criteria for choosing? So they can give you one, two, three, four options, and then they will tell you to choose one of them. Okay, so please be aware and understand what these things actually criterias are important when we are going to choose a grid connected panels. Okay. Uh, these are grid inverters. So these are major components in grid connected PV system like DC inverter is also called power conditioning unit. So this is the power conditioning unit which Nisit you are talking now. So these systems actually have an interface between the inverter and this uh, grid. Somebody wants to join. Okay, so what it does, it basically converts the frequency from the battery storage to sine wave frequency, and AC voltage to be fed into the grid must be in phase with it. So it doesn't mean that AC voltage in the grid is 60 hertz and then you are feeding it with some 100 hertz or 20 hertz. So that won't make a sense. It will lead to losses and the frequency won't match. Then there are several losses with respect to frequency. Also, there uh, all inverters are connected to grid, so they incorporate MPVT, multi-power point tracking system, for these type of grid inverters. Okay, so there are several factors. I don't think these need to be discussed. One thing is there is a term islanding detection. So what happens that in islanding, actually this the island term is basically when you talk of any island term, so island is something which is surrounded by water. So the same type is actually happens here. So islanding is basically a condition, okay, in which the distributed generator, that is solar in this case, continues to power a location even though the external grid power is no longer present. So this can be dangerous actually for the utility workers who go there and work and may not realize that circuit is still powered. So this has to be kept in mind. Okay. So grid and inverters should be able to detect this type of islanding. So there can be several type of inverters like module inverters, string inverters, multi-string inverters, and central inverters. So yeah, these are some of the typical advantages, disadvantages of these type of inverters. So please go into this. These are very important because many questions can be asked in the exam based on these type of inverters. So they can give a list of inverters, then they can list the properties, and they will ask you to match these properties with the type of inverters. Okay. So yeah, multi-string inverters has MPPT. Similarly, string inverter also has MPPT. But there can be question like which of the inverters has MPPT? Doesn't have MPPT. So which doesn't have MPPT? String has MPPT. Module doesn't have MPPT. Okay, so no MPPT is there. So yeah, based on the different types of inverter, these the table here list all those things. So has compiled beautifully these things. So I want you guys to focus on this table. This table is very important. Okay, please spend some few minutes on this table and then we will move forward. Okay, so let's move forward. So yeah, uh, the islanding term which I was saying puts in danger of grid connected system. So basically, we a worker or some electrician may not realize that PV is still producing power, and then this can be a very dangerous phenomena. So yeah, it must be prevented. There should be, though I think most of the electrical engineers or something have someone who has electrical background must be able to comprehend this slide because the cables, there are several type of cables which color coding, the sizing of the cables are also important. So the selection of the accurate size and type of cable would enhance the performance and reliability of the PV system. So yeah, there can be different types of cables. So there is no point going into much detail. So I think most of you are quite uh, conversant with the type of cables, and there are three types of this. This is called three core cable, okay, and their diameter must be mentioned here. So that's why a cable notation is done. So yeah, types of solar cables are there: solar DC cables like DC main cables and modular string cables. Then we have like these type of cable connections are there. Okay, you will integrate the PV panels. So one PV panel is actually connected to second one, and similarly, a range of panels are actually connected with each other to provide a suitable voltage and current. So, yeah, Arvind, do you have any question? Actually, okay, okay. So actually, what is this, Arvind, that we have been refrained from discussing the current assignment questions? So we actually received a mail from NPTEL itself that you don't have to discuss the current assignment questions. So if there is something which is quite problematic in the assignment questions, so you can raise the question on the discussion forum of the NPTEL. Okay. Okay, so no problem, and don't worry, we will solve those type of questions in the this lecture slides also. I think you will be able to solve it. Otherwise, don't worry. You ask it on the discussion forum, then we will have a discussion and then we'll provide the solution. Okay. So there are combiner boxes. So basically these are type of safety and that includes safety fuse or breaker for each string. So a type of like enclosure for the cables and different switches like MCBs, RCCB, etc. So these are connectors. They are different parts that are used to connect cables and all those type of things. So another thing is that we have to mount the module on something. So there can be different type of module mountings like mounting can be on a metallic support or it can be integrated to the building as you can see from the roof here, building here. So wants to join. So yeah. I was discussing this roof mounted. Yeah, there are actually what I will say. I think most of you must be conversant with this also. Like now the PV panels are actually mounted or a floated type of PV panels in which the whole lake is actually covered with the PV panels. The canals are covered with the PV panels. Uh, does anyone of you have or have heard about this? The canal is totally covered with PV panels. So there is a benefit of this covering of PV panels with canals or water bodies with these PV panels. Uh, any one of you want to share anything about that? Yeah, floating PV panel. Mayank Dhar has actually posted floating PV panel. Similarly, Natik has also said yes, sir. So yeah, do you want to say anything on this floating panel? Okay, Natik is saying in our Gujarat, the Narmada Canal. Yeah, yes, you Natik. Yeah. So, what are the advantages do you think is we are having because of covering the canals with PV panels? Very good point. Very good point. Actually, the solar panel, backside of solar panel has severe losses. So there are several losses, and when we lower down the temperature, the efficiency actually increases. So yeah, this is a very good point. Any other point? Mayank, do you want to say anything? Mayank is saying water evaporation reduces. Very fantastic point to stop water from the. Natik, actually, solar energy doesn't convert water to steam directly. Yeah, it can convert it to vapor. So evapotranspiration is there, evaporation is there. So actually, these actually stops the sunlight from directly going to the canal, and that's why this water loss is quite less. In so this can be a very good phenomena when we cover the canals with this uh, solar panels, floating solar panels. So yeah, any other solar panels do you see do you use of unused areas also, because yeah, India doesn't have lots of land, so we have quite a great amount of people living here, so we have shortage of resources. So the panels mounted on the canals are actually utilizing those resources to mount the panels, and also we are getting huge amount of electricity out of those unused areas. So there was a plan. I don't know. I am not very sure of, but there was a plan to cover the this uh, Rajasthan Thar Desert and some portion of the Thar Desert with this, or many power plants to be installed in the Thar Desert. So we because Rajasthan, Gujarat, Maharashtra also to some extent, Tamil Nadu, they have quite a good amount of sunshine days and good amount of solar irradiation falling on the surface. So yeah, these states can actually be promoted to use the solar energy. Okay, so do you know, guys, that this the rover which we have sent on the moon, the Pragyan rover, also uses the solar panels for its energy. So you must have seen the images of Pragyan rover, and there is on the side the solar panels are there. Aditya L1 also, yeah, because in space we don't have anything to generate electricity other than solar. So solar is a very good phenomena to actually solar. If you compare the Earth, the solar energy received by Earth, we are not even utilizing the 1% or 0.001% of the solar energy. So there was a study that if we able to use some 3 or 4% of this solar energy, we will have enough energy to power the whole earth. We don't need to burn the fossil fuels. So imagine if we don't burn the fossil fuels to power our cars or to get electricity, the amount of saving in the carbon dioxide emissions and various other pollutants, how clean our atmosphere will be. So that's why solar energy is important, and solar energy should be promoted for these things. Okay, so let's go to the slides. So I am finding the slides are quite interesting. You guys are learning a lot of things. So yeah, this is what this live session is for, to have interaction with you guys, to know your uh, to have a talk with you guys, to share the knowledge with you guys, and also to get the knowledge from you guys. Okay, so yeah, most of you must have seen this type of the let me take a pointer, this type of ground mounted solar photovoltaic panels on the roof. This is rooftop mounted, so my house also has this type of panels installed. It's a rooftop mounted panel. So generally this there is a concrete system here which actually holds this metallic supports, and then panel is fixed on that. So this is for ground also. You can see the roof mounted. So SCADA systems are basically supervisory control and data acquisition systems. So what we have, why do we use SCADA? So basically we have solar panels spread throughout acres and acres of land. So these solar panels individually and collectively formed a group, and those groups have meters, inverters, weather station, tracking devices, DC strings, substation equipment, everything with this. So these need to be monitored from a central location so that you guys upfront know what is the problem or what is the power output of the system, or do you want anything to be changed, so you can give command to that. So SCADA is actually a supervisory control and data acquisition system for that. It's a combination of hardware and software, I will say. Okay. So yeah, you can see a type of SCADA interface here on the right hand side on this laptop, desktop, and tablet. So weather monitoring system is actually very much important because solar is very much dependent on the weather. If you have cloudy weather, then sun, then this solar output will be very much less. So weather monitoring system can be very much helpful. So this is a typical weather monitoring system. So it has options for wind direction, wind speed, temperature, humidity, rainfall, solar radiation, and barometric pressure. So these are cable glands. These are simple for connecting and joining different equipment, devices, etc. Cable lugs are there, and cable ties, ferrules are there to tie them actually and number them. Cable trays are there to lay the cables on the ground or on the upfront overhead. Then we have lightning arrestor also. So I think lightning arrestor you guys must be aware of this lightning arrestor. The lightning arrestor is to avoid the destructive effects of lightning strikes. So yeah, lightning strike can damage the solar PV cells. Fuse also plays an important role. So in this slide, we actually discuss this layout of grid connector system and different components. So I think most of this you guys will be familiar with, have quite a good amount of knowledge now of this type of system. So I think we should take a break of 1 or 2 minutes. Then we'll discuss the lecture 16 and 17. And in lecture 16 and 17, I will mostly focus on the numerical part. Okay. Otherwise, something interesting is there, then I will go into that. Okay. Okay, so I think you guys have a good break. So let's discuss the concepts now. So I am finding a very good numerical here. So we will go directly to the numerical, but before that we'll discuss some of the concepts related to this numerical, because it is very important to discuss the concept. Until and unless you won't be able to understand the different how this numerical has been approached and solved actually. Okay, so for that, let me share the screen. So, actually, here in this slide, the design of a grid connected PV system. So this is basically a design of a grid connected PV system I discussed here. So when we try to design a grid connected photovoltaic system, so first thing is to do a preliminary study. Okay, so I think most of you were familiar with the terms irradiation and other temperature, these type of things. So yeah, first thing is to study the geographical setting of the location, like what is the addition value, conditions, etc. Analysis of the climatic condition and necessary selection of the system and selection of the PV technology like monocrystalline, polycrystalline, perovskite. These are, perovskites are not so commercial. The selection, then we have to design the system like selection of the components, module, inverter, cables, combiner boxes, then PV, array inverter matching, number of modules, number of inverters, cable loss calculation, shading analysis should be done, and then we go to the performance analysis, that is system energy production and performance ratio calculation and system losses. So these have to be calculated to understand the performance of the system, how the system is performing with respect to the reference system, or what is the performance of the system, is it able to produce the exact current that is required, or the input voltage, sorry, the output voltage that is required. So these things have to be compared, and basically on anything which is designed has to have a specific set of standards of performance that goes into it. So basically, what includes a preliminary study? So first thing is that you determine the solar access to the site, then determine whether any shading is there, or is there any effect, to estimate the effect on the system. Like there can be trees, or there can be some posts, buildings, anything that can have a shading effect on the system. So if there will be shading, there will be poor performance, or you say it won't reach the standard of performance that it has been designed for. Then we have to determine the orientation, tilt angle of the roof side. So if the roof is tilted, so you will have to actually match it with the, so that the sunlight strikes normally to the surface. Then you have to determine the area that is available for the solar array installation. Like if there are lots of area, but you can't install solar array everywhere. Okay. So also you need to determine whether the roof is suitable for mounting the array in case of roof mounted system. So if there is a concrete roof, then most probably it will be suitable for the mounting. But in villages, you see most of the roofs are actually made of thatched, or like some uh, residual biomasses, so that is not very much suitable to handle the weight of the solar arrays, or uh, won't be actually very much suitable to hold the solar array. So if there is any adverse weather condition, this solar array can fly away, straight fly or move with the wind, or if there is any very high wind. Okay, and determine how many modules, how the modules will be mounted on the roof side. Determine where the inverter will be located. Determine the cabling route. This is very important, cabling route. So you have to lay the whole cabling route, and otherwise there can be that you laid the cable in the roads. So when people walk, they will face very much difficulty in walking into the road. So yeah, all these things are very much important. So various parameters are actually uh, like for climatic condition, NASA meteorological department also provide these climatic conditions. So you can go to this website, you can bookmark this website, so you can get a good amount of data from this website. Okay, so the monthly average daily normal radius, I think most of you guys know. So can anyone say about this daily normal radiation, DNI? So if you guys are not, I think it's in the lecture slides one or two. So please have a brush up of the concept, because those concepts will be utilized here. Okay, so you can see the linkage of whatever you have studied in lecture one and two, and these things are actually getting repeated in lecture 17. So yeah, these things, the daily sunshine hours, you calculated the daily sunshine hours with the empirical relation which you use to calculate the daytime. Okay, so yeah, these things are very much important. Then we go for design of the system, like selection of the components. So yeah, so there are various standards also. So what does standards does? Standards actually make us set a benchmark, like this is the benchmark when there will be solar modules. So this is the IEC 61215 defines the what should be the length criteria and what should be the efficiency, how the efficiency will be measured, all these things. Okay, so yeah, these standards are very much important to have a uniform what you say, uniform criteria of measurement throughout the country. Okay, so solar PV modules, inverter cables, then we have connectors, array boxes, and all those important things have a standard, and all these standards have been listed here. Now coming to the designing of the grid connected PV system. So please spend some time on this slide. Then I think you guys must be someone with electrical background will be familiar with these type of terms. So these are not very much like pretty hefty terms. These slides may seem busy, but you can use these equations to easily solve your numericals. Okay, so I will try to solve the questions which is given on the last page of the slides, and then we will apply these formulas, mathematical terms, and we'll solve those questions. Okay. So please try to read this slide till then. Okay, so let's start discussing the designing of grid connected solar PV system. So basically, designing a photovoltaic system is based on an energy balance. Okay, so only one thing you have to remember: the generated energy is equal to the consumed energy during 1 year. So for 1 year, if you are generating some energy, then whatever energy consumed will be equal to. So yeah, the energy at the DC side, that is from the solar module, will be EDC equal to E total current and to GM into N efficiency. So that is the actually total energy yield, and then it is related to area of one module AM equal to A total equal to number of modules into area of one module. Okay, so required energy balance is EDC equal to EL into SF. So SF is basically a sizing factor that is normally assumed to be 1.1. So required number of modules can be calculated by when you are doing energy balance. So yeah, you just equate this with this and replace a total with NT into AM. So just divide this term, so you will get the number of required number of modules. So and yeah, it denotes the ceiling function, the lowest integer that is greater than or equal to x. Okay, so yeah, when there is x, like this values comes out to be 11.6. So lowest integer that is greater than or equal to x is 11. So that will be taken as this number of modules, and number of modules connected in series is ns and in parallel are np. Then it is denoted with nt, that is total number of ns equal to n series into n parallel. So if the nt equal to 11, then it can be taken as 12 because it has to be multiplied. So series into parallel, like 12 can be a combination 12 is to 1, 6 is to 2, 4 is to 3, 3 is to 4, and similarly. Okay, the power on the DC side at STC now be given as PDC equal to N total, that is total number of modules, into power produced by single module. So this has to be greater than, power at the inverter has to be greater than this generated. So nominal DC power of the inverter should be approximately equal to the PV power at the STC. So STC, and in practice the nominal DC power inverter is selectively below the PV power at STC up to 10%. So depending on the climate zone, because different irradiation distributions are there. So PDCO, also for PDCO less than 5 kW single phase inverters are used, and for PDCO greater than 5, 3 phase inverters are advised. So a specification of a 300 watt solar module manufactured by Tata Power. So this is the specification, like power output is 300, module efficiency is 15. Voltage at Pmax VMPP equal to 36.6, and current at Pmax IMPP is 8.2. Open circuit voltage is 44.8. Short circuit voltage is 8.71. Power tolerance is 0 to +5. NOCT is 47 plus minus 2, module efficiency 0.06 plus minus 0.01. The temperature coefficient is 0.4048, 0.2931, and 0.0442. The input data, maximum DC power for a specific inverter manufactured by Bongi Figlioli for this. So this is the input data for the specific inverter manufactured by Bongi Figlioli. Sorry. So it is very important to match this inverter and array to find out the appropriate combination of module and inverter by considering the local operating system. The voltage, current, and power rating of the module and inverter are three criteria which ensure the proper matching of the system in terms of performance and safety. The important steps related to matching of inverter and PV modules are number of modules in a string, maximum number of strings to match with, and matching the power rating. So there are lots of terms and like number of modules in the string and minimum maximum operated effective voltage, operating temperature, all these things have to be taken care of. So if you know the ambient temperature of a particular location, nominal operating cell temperature of PV module can be calculated, and the solar radiation and the location module operating temperature can be calculated using this. Okay, and G is the solar intensity, that is in kilowatt per meter square. So these equations you have to use to calculate the minimum and maximum effective voltage of PV array. So you can use. So it is very important to keep in mind that output voltage of the array should not fall outside the inverter's MPPT voltage range. Okay, so if inverter MPPT voltage range is certain specific amount, then output voltage should be less than that. And minimum number of modules in a string can be calculated using this equation. It's quite a challenging task for designing a photovoltaic system. So this involves lots of equation and yeah. So yeah, there is a formula for selection of DC and AC cable also. So also there is a setting. Setting analysis is a quite important because when modules are arranged in parallel, so one of the modules can cast a shadow on the other module. So this has to be done so that the even the sun is at the highest position cannot cast a shadow to the next solar cell. So these are the empirical relation that can be used to actually determine the length of the shadow and various other things. So this can be quite tough, challenging question. So solar power plant is to be installed at IIT Guwahati campus to meet the electricity demand of 2 megawatt. Okay, so yeah, there is a requirement of 2 megawatt at the solar insolation of. So IIT Guwahati has a solar insolation of 800 watt per meter square. The manufacturer's output tolerance derating due to dirt and duration due to temperature of a PV modules are 5%, 5%, and 0.5% per degree Celsius respectively. DC cable losses, inverter efficiency, and AC cable losses are also there. The inverter has a maximum voltage of 900 watt and maximum DC current of 600 ampere. A detailed specification of the module and inverter are given in table 1 and 2. The minimum temperature, maximum temperature on solar peak hour of site is reported to be 5 degrees Celsius, 38 degrees Celsius, 5 hours respectively. Find out the total number of modules required for the plant and also estimate the DC power. So from the specification of the modules, like we discussed for the Tata and Bonji field only, we know these values, we know specification, technical specification of the inverter, we know. So these have to be used. T minimum is given 5 degrees Celsius and T maximum is 35 degrees Celsius. Okay, NOCT is 47 for the module. Okay, so NOCT you know. Now this is the array, so it has 800 watt per meter square. Then power is generated and it goes to the inverter coupled with MPPT. Then grid 2 megawatt. Okay, so you have to obtain the operating temperature. So ambient temperature at 28 degrees Celsius. It's mentioned here. Ambient temperature is somewhere mentioned here, or if not mentioned here, then you can assume at ambient temperature. Okay. NOCT is given, so T operating temperature is calculated. And the rated PV power output is PSTC into F temperature into F dirt F empty. So putting the values PSTC, that is from here 300, where it is from 300 power output 300 watt. Then we multiply it with efficiency 0.85, 0.95 and 0.95 from here. Okay, so these efficiency are given now, output tolerance and dirt, and so okay, so you just decrease it from 100 and multiply it. So 230.17 watt is the PV derated. So and then there is a STC of 25 degrees Celsius and 0.5% of power is lost per degree Celsius. Okay, here it is mentioned derating temperature. So based on that, you calculate the other parameters like TO minimum and TO maximum. So minimum is 32 degrees Celsius, maximum 65 degrees Celsius. And using these formulas, which we learned here, these the relations actually, these number of modules in a string. So put these values here in this and get the values of minimum effective voltage, number of strings is 12, the maximum number of string is 22, and then the current short circuit effective current 8.69 ampere, the maximum number of string is connected to pin 11. Okay, so S max is actually 69. So based on that, there can be various combination. So if number of modules are 12, that was calculated earlier, so there can be various combination, and based on that you just have to multiply it with 12 into 69 into 300, then this is the power output and this is the directed power output. So you just have to see the output of the this inverter is 280 kilowatt. Okay, so the point at which it touches the 280 kilowatt, so next point is 281, so this is the minimum number of string. Okay, similarly you get it for this maximum string also. So that's how for 2 megawatt the number of modules will be 7392 or 9698. Okay, so minimum and maximum modules are actually given. So with this we have designed the solar PV and various formulas. So these can be a very complex actually. When I will try this question, so I will also have to take a lot of practice to solve this question. Okay, so it's not so easy, you need practice to solve these questions. There are lots of formulas, and please remember these formulas. They may not be given in the exam, so these are very simple formulas, so you may need to memorize them. Okay, so there can be questions based on that. The similar ones in the assignment question, you can expect this on the same terms in the exam. So we'll discuss some of these concepts here. So I think the majority of the concepts has been discussed, and how to design a solar photovoltaic grid and the whole modules of array. So after this, we will also have performance analysis, how performance analysis will be done. So I will not go into detail of this performance analysis thing. I will just touch up on the basic thing which is required to actually analyze the performance of a grid connected photovoltaic system. Okay, so please have a look and please go through the content in the lecture 16, design of solar PV system. Okay, so without going into much detail, just have a quick recap of the performance analysis of the system. So yeah, so what can constitute a performance analysis, like annual yield, reference yield compared with the reference yield, system losses, temperature losses, all these things. Okay, so yeah, AC energy output. So these are the like efficiency of the system is calculated as power, instantaneous power output from AC side, and total power generated. Okay, so these parameters are actually used to calculate the efficiency and performance analysis actually. Then there is capacity utilization factor, that is defined as the ratio of actual annual energy generated by the PV system to the amount of energy the PV system would generate if it operated at full rated power for 24 hours per day. So actually the main problem here is that ki capacity utilization factor is quite low, quite very low for solar power. It's zero point 0.3 or something. Here it's given rooftop it's 16 or 17%, but for solar power plants it's 25 to 30%. Okay, basically because it doesn't generate, it is considering 24 hours of electricity generation. We don't have sun for 24 hours, we have sun for only 8-10 hours. Okay, so that is the, we have clouds, rains, all those things. AC capture losses, system losses, energy yield. So these are the formula which you need to remember. Just put the values, get the answer. Most of the numericals are based on these formulas. Energy yield of the system, system losses, derating modules. Yeah, I think we don't need to discuss each and everything here. So, yeah. So let's go to the assignment questions of the previous run of this course. That will be more important for you guys. So the first question is, in a grid connected PV system, the maximum DC power output of the PV array is less than the input DC power of the inverter. The maximum DC power output of the PV array is less than equal to input DC power of the inverter. The maximum DC power output of the PV array is greater than input power of the inverter. So what can be the correct answer for this? So actually maximum DC power output of the PV array should always be less than the DC power of the inverter. Okay, so only option 2 is correct here. It's not greater than the where is the cursor? Yeah. So only option B is correct here. Okay. The ratio of actual energy generated by PV system to the amount of energy generated by PV system under full rated power for 24 hours per day. So we just discussed this term now, capacity utilization factor, and what is it for household? 16 to 17%. Okay, so the correct answer is answer C. Which of the following statement is and are correct? A grid integrated solar PV system always receives power from the grid. A grid integrated solar PV system supplies as well as receives power from the grid as required. The grid integrated solar PV system always supplies power to the grid. The grid integrated solar PV system works only on the grid phase. So this is incorrect. Always, it doesn't supply always. Capacity utilization factor is low. Now, how can it supply always? A grid integrated so always receives. It doesn't receive always. So there is some power generated by the PV system. So it doesn't receive power always. So yeah, supplies as well as receive power from the grid. Only option 2 is correct. So yeah, I won't be discussing this MPPT. It's just like diagram for what an MPPT is. This is standalone system. Okay, grid connected as inverter. A 8 kilowatt system produces an average electricity of 8850 kilowatt per year. The specific yield of the system is, so guys, what can be the specific yield of the system? So there are formulas for this. Okay, so don't panic. Okay, how can you calculate the specific yield? So what is the yield? 8850. And how much is the system? 8 kilowatt. Okay, so just divide it. So you will get 1106. So the correct answer is answer D. A PV module has a VMP, that is voltage at maximum power is 38.5, and a VMP temperature coefficient of 0.19 volt per meter. The maximum cell temperature is 75 degrees Celsius and the ambient temperature is 25 degrees Celsius. The minimum expected voltage of the module is. So using the formula, just put the values there and you will get the minimum expected voltage of the module to be 29 volt. Okay, so how can you calculate it? So actually voltage at maximum power point is given equal to 38.5. Okay, so I am solving this question for you because most of you say that we are not able to solve the numericals. But I won't spoon feed each and every question to you. There are formulas. You just put the values and get the answer. So let me try and solve this question for you. So voltage at maximum power point is given, V equal to 38.5, and voltage temperature coefficient is given 0.19 volt per degree Celsius. Okay, and maximum cell temperature is given 75. So now the difference between cell temperature and HTC. So what is the difference between cell temperature and HTC? So HTC is 25 degrees Celsius. So divide minus it from 25. So this difference is 50. So again effective voltage will be 50 into 0.19. Okay, that is 9.5. So minimum expected voltage will be, that is asked in this question, minimum expected voltage. So what was the voltage at the maximum power point? 38.5 minus 9.5. So the correct answer is 29 volt. That is A. Okay. Now the PV array consists of two strings. Okay. So two strings are there. MPP of one string is 216. The current in one string is 5 ampere. The distance from the junction box to the inverter is 10 meters, and the minimum string size cable is this to meet the 1% voltage drop. So what do you say? Let me solve this question for you also. So see, try to see how I am solving this question. First, you need to identify the data given in the question. When you identify the data, you will be able to solve most of the question. Okay, so data is given, MPP is given, so write it, MPP. How much is that? 216. And current in the string, okay, it's given 5 ampere. Resistivity of copper is given 0.0183, and the units, okay, ohm per meter per millimeter square. Okay, length of cable is given equal to L length. Okay, I'm not writing totally, so it's 10 meter. And voltage drop should be given. Yeah, it's given, equal to 1.5%. So minimum size of the cable, just apply the formula. Minimum size of the cable formula, you know na, 2 into this length of cable 10 meter into IDC, that is 5, into resistivity 0.0183 divided by loss. What is the loss? 1.5% is the loss, so in actual loss will be 0.015. Okay, divided by 100 into voltage of the string 216. So calculated, it will be 1.12 millimeter square. Okay, so minimum size of the cable string is 1.12 millimeter square. Now there is a data given, and then you have to solve the questions. So this is actually also a formula based question. I think the same type of question was also solved in the previous numericals also. So you just have to apply the data given, and that's all. You will get the answer. Okay. So I think they are asking specific energy yield and actual DC energy, and then performance ratio of the power system. So you have the formula from this, no? The last slide which I discussed. Okay. So just apply them. It's not a very difficult question to start with. Or do you want me to solve it? Do you want me to solve it? Okay, let me solve. Should I solve all these three, or I think the time is permitting to solve all these three. Okay, I will solve all these three. Then 10 and 11 and 12 you guys will solve. Okay, because I these questions are very easy. I think this was based on the design, the question which we discussed in the slides. Okay, so based on the design you have to solve it, because the data is given for the module and specification of the inverter. So it's a very long question. So if I try to solve it, it will take half an hour or 45 minutes. But this is very important. Okay, so just try to solve it. Try to do it by yourself, and you will be able to solve this type of question. The more question you practice, the more you will be. And question 7, 8, 9 I will solve. Okay, for you guys. So please see how I am solving. Okay, number of modules is given 40. First write the data. STC is given. How much STC is given? 315. Mind the units, okay? Manufacturing tolerance is given 6%. So let's say M T equal to it's 6%. So MT will be 0.94. 100 minus 6%. Okay. And dirt derating due to dirt is given also. So derating due to dirt, uh, let's say D derating due to dirt, so it's given 7.5%, so it will be around 0.925. Okay. And derating due to temperature, so it's also given minus 0.5 degree per Celsius, so minus 0.5, so write it as it is 0.5 degree per percentage per degree Celsius. So this is actually separate. Okay, and then the ambient temperature is given 34 degrees Celsius, and if ambient temperature is given, then multiply it with this 0.5 degrees Celsius which is given here, so you will get the voltage drop. So multiplying 0.5 into this, so it will be around 17%. So 100 minus 17% will be 83%, that is 0.83. Okay, so you have to consider 0.83. So now the actual DC energy output from the PV array. So what is the output, specific output, STC rating 315 into what is the this 0.94 manufacturing tolerance, and you have to the rating due to this dirt and temperature 0.925 into this ambient temperature thing 0.83. Okay, into number of modules is there 40, and number of hours of operation is there 4 hours. So multiply all these things. Okay, so if you multiply all these things, you will get the values in watt hour. So divide it by 1000, you will get kilowatt hour, because it's asking kilowatt hour. So answer, if you multiply all these things and divide by 1000, the answer will be 36.37. Okay, you can do it and calculate. Okay, so correct answer is this. Now the next is specific energy yield of the system. So that is again a question. The specific energy yield is basically you need to calculate the AC power for that. So AC power, so DC cable loss is given 4%, then inverter efficiency is given, and then AC cable loss is given. So you have to multiply 4% is 96% is there, 95% is there, and 98% is there. Okay. So just if you calculate the actual AC power, it will be this DC power 36.37 into this 0.94, that is taken from, sorry, 96, into 0.98, that is inverter efficiency, and then we have AC cable loss, that is 0.9. Inverter efficiency was, sorry, it was 95%, so 98 is here, 95 take here. So calculate it, it will be 36.37 into 0.96 into 0.95 into 0.98. So that will be around 3 point, it won't be, it will be around 30 point, no, let me think, 36.37 into 0.95 into 0.96 into 0.98. So it's around 32.51. Okay. So this is actual energy AC power. Now to evaluate the specific energy, you need to know the for 365 days. So it will be, multiply it with 365, 11864. So for yearly it will be 11864.71. Okay, and divide it by the number of hours of operation, that is 4 hours, for determining the specific energy yield. So 11864 divided by 4, something 2966, it's coming 2966.18. So I think I must have done some calculation mistake. Okay, so you guys please refrain from any calculation mistake. So let me check again. I think it's the actual DC energy electricity 36 0.96, yeah, 0.95, 0.98, and 32.51, and it is multiplied it with 365 and this, and then we divide it by P array STC. P array P. So I think I must be doing something wrong or something, I don't know. Wait. 11864.71 divided by 350. I don't know. I may be doing something wrong. Okay, so there may be some calculation mistake. Okay, so this comes out to be 2966 or something. Okay. On the next question is performance ratio. So performance ratio is basically E actual which you calculated upon this E ideal. Okay, so E actually you calculated this much. So what should be E ideal? So E ideal power is, so I think this has to be, wait a minute. 11864 and it's 13 or something. Okay, so I'm not getting actually here, but you need to calculate the E actual you have calculated it here. Then you need to calculate the E ideal, that is energy calculator ideal. So that should be 40 into the 4. Okay, into 365 into 13 or something and divided by 1000. Then this will be ideal, then actual, and then the when you put all those values, the answer will be answer B. Okay, so I think I've solved most of the questions here, and the rest of the questions should be done by you. Most of the questions are quite easy. When you refer the numerical formulas, we will be able to solve it. Okay, so if there are any difficulties, you can please write to me at this email ID. So I will leave you guys for some time to this question if there are any difficulties, so you can have time to ask.